Okay, so welcome to another seminar. Today we will have a very interesting talk on expressive power of regular expressions, but not normal regular expressions, but the subroutine calls and lookaround assertions. And Ondřej Guth will tell us what that means.
Thanks. Classical regular expressions from 50s are some very old construct to describe basically regular languages. So when we stick to the very old classical hierarchy of languages, regular, context-free, context-sensitive, recursively enumerable, regular expressions are exactly regular languages. This example of regular expression is or says my great grandfather, for example, or great grandfather, because plus means alternative, asterisk means repeat. Okay, so this is classical regular expression. But regular expressions seem to be great in pattern matching, and pattern matching is implemented in many tools. In those tools, what we can see is not exactly the same syntax of the classical regular expressions, because in those regular expressions, we can only use this concatenation, putting things one after each other, repeating and alternating, and nothing else. But in real-world tools, there are other things we can use. For example, some restricted repeats, character sets, etc. And the problem is that in every tool, the syntax and semantics is a little bit different. They are not unified, and they are definitely not the same as the previous theoretical model. So for instance, if we take this library used, for example, in PHP language, we can use this subpattern recursion. We basically say when we encounter this sub-expression, we can repeatedly match whatever is in the first parenthesis. So this way we can describe language which is not regular, the same number of A's and B's. So the question is, okay, so we know that we have something with extended syntax, and what can we match? So what are the problems we can match with them, and what are the problems we cannot? With classical regular expressions, it's simple. It's when it's regular language, we can. When something else, we can't. But here it's open question. Even though these tools are decades old, we still don't know exactly the answer for this question. What we do know so far is when we combine some features together, for some of them, for some of those combinations, we do know. So if we take classical regular expressions with concatenation, repeats, and add character classes, it is this. So it says uppercase M or lowercase m in this first position, or if we use internal quantifiers, which is basically restriction of the asterisk. It only says this grade can be there once, 2 times, or 3 times, and also concatenation alternative. Then we still stay in regular languages. So these things are basically just syntax sugar, just to make the expression shorter or more readable. Okay, there are other things. For example, lookaround assertions. Those are lookahead and lookbehind. What does it mean? Lookaround assertion is basically a condition. We can say what we expect in some position, but it doesn't match. What's the difference? For example, when we say these girls in regular expressions, just like that, when it's matched, it means something is consumed from the input, so it's not matched again. It isn't there again, and we continue with matching something else. But when we use this lookaround assertion, it is just checked whether this substring is there in the position. But after the check passes, we continue from the position where we were before. So it's like when it passes, it's like it's not there at all. It's the same effect. When it doesn't pass, the matching stops because it means that there is some problem. So we cannot match in that position. So if I examine this example, it says, okay, this question mark means the S before is optional. It can be there or not, it doesn't matter. So it says, okay, girls need, and that after this D in the input, we use this look behind. Look behind means that from current position, we go back and we start basically we need to find this substring as space need before this position. So we basically go back and see if there is as space need. Or this is or L need. So we basically want to find L need, and then there can be S, which is actually matched. Yeah? So this is basically just the check for the S symbol, if we can find it there or not. Okay, so if we extend classical regular expressions with lookaround assertions, we are still within regular languages, so they don't extend expressive power. Other thing is back references. Back references are maybe the most common features in the real world tools. Here there is a pair of two important things. One important thing is they usually call it capturing group, which is just a set of parentheses. And whatever is matched within parentheses is recorded in some memory. And then we can refer to it with the back reference. So this says, in this position, we expect to be repeated whatever was recorded in the previous parenthesis or in the first parenthesis. So this can match, for example, with 20 A's, because the first 10 A's are within the parenthesis and the second 10 A's are for the back reference. Okay, so this is quite well known. This seems to be like the well-known language, the two substrings, repeated after one each other, which is context-sensitive language. Context-sensitive language is this class. And also, we know that with back references, we cannot match some context-free languages. So it's basically incomparable to context-free languages. So something from here, but something not from here. Okay, so this is just back references. Okay, and then there are some other results. For example, if we combine back references and lookaround assertions, it is known that such expression can match something more than just back references. So it's quite interesting that in context of regular expressions, lookarounds do not extend anything, but in context of back references, they extend the expressive power. Quite weird, but true. Okay, so well, if we want to answer the question what we can actually match with some implementation and to make some mathematical proof, it could become somehow challenging because, well, we can just, okay, it's maybe impossible. So what is happening actually is that we start with mathematical model of that implementation. So there are several formalizations of regular expression or of the implementations. One of them is called matching relation, but there definitely exist others. So the definition is that matching relation is a triple of regular expression, input string, and current position. And the matching result is basically the set of positions in the input string we get after successfully matching this regular expression and this string starting from that position. Of course, the set can be empty if there's a mismatch. And then the language of regular expression is all the strings which can be matched starting from the position 1 when we get, well, past the input string. So we can read it all basically with the regex. Okay, some more concrete example. Basically how it works that way that we get some expression and we split it to pieces and try to find some trivial sub-expressions for which we know the answer, and then we combine it back and know the result. So some trivial example is just a symbol. So how do we match a symbol? We basically just check whether that symbol is in that position or not. If it is, we advance the current position. Otherwise, we return just empty set. Or, for instance, how lookahead is defined in matching relation. We only check whether the sub-expression matches in the current position. If yes, we stay in the same position, because remember, lookaround is only a check of a condition, but it doesn't consume anything from the input. We continue from the position where we were before. Well, matching relation already existed for 1 year, and it was defined for some of the features used in real world implementations. So there's task to extend it to some other features. For example, subroutine call. When subroutine call basically means okay, I just need to remind you what it is. Some example, yeah, this is subroutine call. So subroutine call means we match again some sub-expression from current position. Yeah. So this says, because this means first pair of parentheses. So when we hit this position, we basically start matching with this parenthesis again and again and again and again, because it's inside. So it is one way how to introduce recursion in regular expressions. Other thing is, well, so they are numbered, which basically refer to the set of parentheses when we count them from the left to the right. I mean the opening. Or in some flavors, there are also named parentheses and named subroutine calls. So we can refer to some set of parentheses which have some name different than the number, and then they can be combined together. Well, so just to make it more understandable how matching relation works, because I know this is too abstract and maybe this is too concrete, but let's see. So let's have this expression starting from the red parenthesis and ending with this, I don't know what color it is, something greenish. Just not black, this one, yeah. So first, what do we have here? I try to explain in words what it means. Okay, so this define parenthesis, what it is. It basically says we just introduce whatever is inside to the regex. So basically, the engine knows about it, but by itself, it doesn't do anything. Yeah, this is basically conditional, which is always true. So whatever is in the red parenthesis, well, it is good, it is there, but it doesn't do anything by itself. But how can we use it? We can use it by subroutine call, because we can say, okay, I want to match parenthesis which is named S, which is here. So basically, I call this parenthesis, hey, start matching this. So it starts happening. Yeah. So what it does? Well, let's examine it. So here on the top level, we can see concatenation of two things: the define rule and the subroutine call. So on the left, there's the define rule. Because define rule doesn't do anything, it just returns the same position we started at. So we are still in position 1. and concatenate it with the subroutine call. So we need to examine the subroutine call. Okay, so the subroutine call means we just go in the name parenthesis and use the internal as the regular expression we are matching. So it is this A something B. Okay, again, this is a concatenation. So we match A, we match whatever is inside the parenthesis, and then we match B. So whatever is inside the parenthesis, what it is. So it is alternative of this subroutine call for the first parenthesis and the empty string. So yeah, so again, the alternative just means we match one, we match the first one, we match the second one, and we basically make union of the results. Because the result is just position 2, yeah, so that's why we use position 2. So the matching relation basically is used as some derivation. We start with the complete regular expression, and then we use some basic operators to split it to pieces and try to match those sub-expressions. And again, if we don't know how to do it, we just split it again, unless we get something very trivial where we know how to compute the result. Okay, so the main point here is to show what is the expressive power of subroutine calls. And spoiler alert is that it will be context-free languages. So just to remind what context-free language is, there are two quite good examples. One of them is a structure of pairs of parentheses, opening and closing. So the language which contains the correct pairing, so the same number of opening and closing parentheses nested in the right way. That is quite a good example of context-free language. Or other types of context-free languages is palindromes. So something is there and then something inversed is after it. Again, maybe nested within one each other. It is still context-free language. For the proof, we need context-free grammars, because the definition says that whatever is generated by context-free grammar is context-free language. Or on the other hand, for every context-free language, there must exist some context-free grammar which generates it. So context-free grammar is just a quadruple of set of non-terminals, the input alphabet, set of production rules, and starting or initial non-terminal. And every production rule of context-free grammar looks like this. So we, on the left-hand side, we have a non-terminal, and on the right-hand side, we have just arbitrary string. It's not restricted in any way. How does this generate anything? We basically we basically generate some sentential forms, some intermediate strings, and whenever there is some non-terminal in that intermediate string, we can replace that non-terminal with the right-hand side of the rule. The non-terminal is on the left-hand side. So this way, iteratively, we can generate some strings. The result, the string we consider to be generated is only such string which doesn't contain any non-terminal. When it contains non-terminal, it's still just sentential form, not final. So yeah, it's just example. In every grammar, we start with the initial symbol, and then we can just replace it with the right-hand side of a rule. And we can do it again and again and again. So I can replace the S symbol again with the right-hand side of the rule as long as I want, or I can replace it with other right-hand side of that rule, like empty string. So we get AABB. So like that, every context-free grammar works. Okay, so the first part of that proof is we can convert any context-free grammar to regular expression with concatenation alternative, define rule, named parenthesis, and subroutine call. So these are basically sufficient operations. So the conversion goes that way, that we start with, of course, we get the grammar, and we do a straightforward conversion. So empty string is just empty string in the regular expression. Maybe you might not have seen any empty string symbol in some real world tool. It's because empty string is expressed just by nothing, so there's no special symbol. Here I use epsilon just to show that there is something, but this epsilon means nothing written in the literal. So we convert empty string to empty string. Any symbol of of the input alphabet to the same symbol, and the only thing where we need to make a more effort is whenever we see a non-terminal variable, we replace it with subroutine call, and that's all. That's basically the conversion. I hope you can see that this is really one-to-one. We just take the right hand side of the rule and make this from it. And there is nothing else which can appear in the grammar. So this way, for every non-terminal we have in the grammar, we do a conversion of the right-hand side of every rule where that non-terminal is on the left-hand side. After that, we create a named group for that non-terminal. So we started with the S non-terminal. We create named group named S, where the contents of the named group is the alternatives of the right hand sides of the rules, just that. And of course, finally, this expression would do nothing because the defined rule doesn't match anything. So of course we need to start it. We started with the initial non-terminal of the grammar. Yeah, so we can convert any context-free grammar to regular expression, which does the same thing, which matches the same languages using this simple, I hope simple, algorithm. I hope it can be seen that that the grammar and the expression converted this way does the same thing, so it matches exactly the same strings. Of course, there's some paper where some proof, but I hope it is. I hope you can believe it. Otherwise, we can discuss it, of course. Okay, so what do we know so far? We know that these regular expressions, these subroutine calls, can match any context-free language, and maybe more. Okay, so the question is, what is the set of all languages we can match by this? So let's go the other way around. Let's go to conversion of any regex to context-free grammar. So let's say this is our example regular expression, quite complicated, I know. So we can use a construction which was invented, I guess, in 50s again, construction of or conversion of finite automata. Finite automata to regular expressions. It is the Thompson's construction or Thompson's pattern matching algorithm. So this is somehow inspired by it. What we do, we split the regular expressions to the smallest pieces possible again. So we start with some basic constructs like the empty string, the input symbol, the subroutine call, and again, nothing else can be there. Yeah? And then, of course, concatenation and alternative. So we create sub-grammars for all these sub-expressions. So grammar for the empty string, which just generates empty string. Grammar for all the input symbols. Each of that generates just that one symbol. Then grammar for the subroutine call, which just generates some non-terminal, which of course then we need to make sure corresponds to some named group, or group named the same way. So these are some, primitive sub-expressions. Then we need to join them together using those, higher level constructs, concatenation and alternative. So for concatenation, we basically generate a grammar or create a grammar which generates the concatenation of starting symbols of some other subgrammars. Yeah. So this way we iteratively create, and yeah, of course, for alternative, yeah, the same thing. We basically supposed we already have, created grammars for sub-expressions we are now joining together. Now we can join them together. So alternative, it means one or other using those initial non-terminals. Because there is no other construct possible in that type of regular expressions, and define rule doesn't do anything, so we can almost ignore it. Again, this way we can iteratively construct the grammar for the whole expression, which expresses the original language. So the Thompson's construction is the majority of this. What is introduced here as a new thing is the subroutine call. So okay, this part is what is added to Thompson's construction. The remaining part is already known for some decades. So if we believe this, that it works, then we showed the conversion in two ways. So we can say that that the language of regular expression with concatenation alternative and subroutine calls is exactly the set of context-free languages. So here we could somehow relate it to some well-known language class. Okay, but this is not all, because if you remember in the beginning, I told you that if we take lookaheads and lookbehinds, they do not express expressive power of classical regular expressions. But if we add them to back references, they do add or extend expressive power of back references. So the question is whether they can do the same thing with subroutine calls, and the answer is positive. Yes, they can. Here I have proved by example. So there's an example of language. Okay, this language is maybe the simplest context-sensitive language, which is not context-free, because in context-free languages we would be okay with the same numbers of A's and B's. But if we add the third group to it, it is beyond context-free languages. So how does this ugly thing match this context-sensitive language? Well, we start with look ahead. Again, look ahead, just to remind, look ahead is a condition. So we match whatever is inside that condition. But after successfully matching that condition, we start the position. We continue matching from the position where we started. So it's like it wasn't there at all. So this condition is okay. Here, this red construct basically means the same number of A's and B's. How do I know it? I start with A, then I can continue either with nothing or with repeating the first group. So then I can repeatedly match some number of A's, and I like start going into some recursion. And when I return from that recursion, I need to match the same number of B's as A's before. So that's why this is, yeah, the same number of A's and B's, followed by one C. Yeah? So this way, this look ahead basically covers this part of the string A's and B's, the same number, and then some C. So this makes sure that there are no more B's than A's. Yeah? And also there are no less B's than A's. They must be in the same number. So this is just a look ahead. So after we exit this parenthesis, we start matching again from the beginning. So we start matching with A's, and so we need to have at least one A. And then we go into this N2 group, and this N2 group basically says the same number of B's and C's. And all together, because the same number of A's and B's and same number of B's and C's. There's also some classical proof from, I guess, 70s that this really means this language. So using just subroutine call and lookahead, we are able to match some context-sensitive language which is not context-free. So I hope this proof is enough, or this way it's enough. Okay, so I see I'm maybe faster than expected. So if I sum it up, what we have seen so far is extending the current knowledge, what we can express with some particular flavor when we limit ourselves to combination of some particular features of that flavor. The flavor I am referring to is this parallel compatible regular expressions, or also parallel expressions, which are really similar because they seem to be very rich in features. So there is definitely space for research. We have seen only some of the features. We have seen only concatenation alternative subroutine call. And we have seen that they can express exactly context-free languages. When we take this and add look ahead or look behind, because they are quite equivalent in this sense, we go beyond context-free languages. So we go to some maybe context-sensitive languages, maybe also beyond. It is not known so far. So obviously, what can be done in some future research is to find out what exactly can be expressed by the lookaheads combined with subroutine calls. It might be context-sensitive languages. It might be something less, but it's not known so far. Okay,
so let's thank the speaker. Any questions? Okay, so I have a question. When you say that with the lookaheads, it might go like it goes beyond context-free. Do you think like there will be some example of a language that's not context-sensitive, and it will still be possible to measure? Do you expect that?
Well, I don't think so, because I think I'm on a good way to prove that any such expression can be converted to linear bounded automaton. So I don't think so, but the proof isn't complete, so I cannot say exactly. So I don't expect it. Yeah, that's my answer. Thank you.
Okay. Any more questions?
So maybe just one note about the syntax with the subroutine. So is it possible that maybe can you give us an example of the subroutine code?
Yeah. Something
simple.
simple.
So here it seems to me that the subroutine is code even before it's defined. So does it even make sense, or?
Yes. Yes, this mathematical model tries to work the same way as the implementation. And in the implementation, when you have some named parenthesis, it is registered there, and it is basically recognized before matching. The pattern is always compiled before the matching starts. So this named group is there. So yes, it makes, or it works really. It really works that it is matched. This matches this group. It's even written in the documentation, so it's probably intended feature.
So basically, that can be some cycles. So I have to be like able to recognize that it doesn't make sense, or there can be some.
Well, yeah, you're right. The cycle where there will, well, it is a recursion definitely.
But for example, the define always has to be on the top level, right? It cannot be on.
No, it can be anywhere. It doesn't matter. Yes, that might be weird, but it is how it works. Yeah. What can be weird, for instance, if you introduce the same named group twice, then in some implementations it's possible, and then it works. What I've seen, and it's not documented usually. When it works, then it works that you know, the leftmost parenthesis is used. Yeah? Also, this mathematical model does it. So you know this. Yeah, this means, you know, we use the leftmost parenthesis. Sorry, this means we use the leftmost parenthesis named n. Yeah. Because it's how the real implementation works. And PCR, yeah, PCRE at least works that way.
Okay, any more questions? So let's name the speaker again.